So hello everyone, welcome to the 11th tutorial of the course Introduction to Classical Mechanics. So today we will do some problems related to variational principle, and we will do something on phase space diagram. And as this course is coming to an end, I thought it will be a good idea to do some revision. That's why I have included some revision problems from Lagrangian Hamiltonian mechanics, from central force, as well as from moment of inertia chapter. So those we will do later in this video. So as a first application, we will do something from variational principle. In the last video I have done some problems. You have seen I have calculated what will be the extremum path in a flat surface as well as in a spherical surface. And today we will do one thing. It is a very practical problem, which is we will determine the path on which a particle, in the absence of friction, there is no friction, and the particle is moving from up to downward direction, it is sliding, and gravity is acting in the system. In presence of gravity we will deal with this problem, and we will try to find out what is the shortest distance, shortest time for which path, which will be the path for that the time will be shortest. So this is the statement of the problem. Now let me use a blue color. So this is the system. Suppose the particle slides from this point O, and it is going through a path OP1 as shown in the figure, that arc type path, and we have taken the x direction and y direction as shown in the figure. So from the energy conservation equation tells us that kinetic energy of the particle at P minus the kinetic energy of the particle at O, that is equal to the work done by the particle from moving from O to P. Now this P point is some point at a time t. You can think of like this. So it is the position of the particle at any time t. So we can write this according to the energy conservation equation. And from there you will get this equation. So today I cannot do the problem live, because I had met an accident, and that's why I am not very comfortable to write today. That's why I have written it from earlier. So just follow, I will tell you the steps. So this kinetic energy difference between kinetic energy at point P and O is half m and v square. V means ds dt, where ds is the elemental length of the path. You can think that this is the ds, elemental length. And so this ds also can be written as dx square, root over dx square plus dy square, because for this small part, if you consider it ds, so this and you consider it a right angle triangle, so ds square is actually dx square plus dy square. So this type of triangle that is making, so this is dx, it is dy, and this is ds. This is same as that. So that you can write. So the time which we are interested in, so the time, let us say, is capital T, that is 0 to t dt. And this dt can be expressed in terms of length from this equation, because this equation tells you dt is equals to ds by root over 2gy. That just that I have substituted here in place of dt, and the integration limit will be 0 to x1, because our ending point P1 is at x1, y1. So, and if you do this integration now, and I have replaced that ds by root over dx square plus dy square, which can be written as 1 plus y dash square dx also, if you take dx square common from the under root. Y dash means dy dx. Okay. So exactly that has been replaced in place of ds, 1 plus y dash square dx. Now this is our I, this is our f. Okay, so f means that f, I am comparing it with the Euler's equation. So this the situation that capital I equals to f x y y dash, I mean f is a function of x y and y dash dx. So our main motto was to extremize this capital I, and for that condition we get, this was our condition to get the extremization. Okay, so for this problem, for this particular problem, our f is actually this function, that is root over 1 plus y dash square by root over y. That is our f for this particular problem, and we want to extremize this this thing. Okay, so here I have not used the actual Euler's equation. This is the Euler's equation, but I will encourage you people to do it. I mean, from this actual Euler's equation, by some algebraic manipulation you can reach to this particular equation. This is also a form of Euler's equation. Just some algebraic manipulation you can do it. I just use this method to give you some idea of the other forms of Euler equation. You can do solve the problem with from the first equation also, but if you use this second equation, let us say 1, this is 2, 1 and 2 are equivalent, exactly equivalent. So if you use this second equation, it will be a more simpler in the sense. So just try to derive equation 2 from equation 1, it is the same thing. So in our problem, if we focus in our problem, our f, it is independent of x. Okay, and if we focus on the equation number 2, we can see that, so this del f del x, which is the second term of the equation, it will be 0 because that there is no x dependency for our f. So the equation will be f minus y dashed del f del y dashed is equals to constant. Okay, because ddx, I mean if you take derivative with respect to x, that is that will give you 0. So it will be y dash, I mean d dx y dashed sorry, f minus y dash del f del y dash equals to 0. That will give you f minus y dash del f del y dash equals to constant. Okay, so I have just used this thing, and c is the constant. So f, this was the f minus y dash del del y dash of f. Okay, just that thing. I have just replaced my f according to my problem. So now if you do this integration, I mean if you calculate it and do the differentiation, just follow these lines. So here root in the second term, the root y in the denominator is the constant as a I mean it is not a function of y dash, so the derivative will only work on the numerator, and if you do the derivative accordingly, we will get this expression, and from there you will also reach to this equation. This is just algebraic calculation, and if try to do it, and if you are confused, then try to, I mean by pausing the video you can reach the equation and compare it with my equation. Okay, so this will be your equation. Y dashed is equals to a minus y by y under root. Here a is 1 by c, as c was a constant, that means a is also a constant. Okay, so we got our equation in terms of dy dx. Now we will integrate it to get our x. Okay, so dx, so from here dx means dy by this factor what was in the right hand side. So that I have written, and I am doing just the integration. Okay. Now to do this integration, one substitution is needed, that is y equals to, just a second, y equals to a sin square theta. So this is pretty straightforward to do it, and just substitute that accordingly. Substitute your dy in terms of d theta, so you will get this equation, which is the final result. X is equals to a by 2 2 theta minus sine 2 theta. Okay, now as a is a constant, you can define a by 2 equals to b, which is also a constant, and we are defining 2 theta as phi. Okay, so this x equation can be written as like this: x equals to b phi minus sine phi. And remember, we have substituted y equals to a sine square theta. So if we write y also in terms of this, so this will be the result. Okay, because y equals to a by b is coming from a by 2, and 2 sine square theta means 1 minus cos 2 theta. That's why you are getting this equation. So x equals to b phi minus sine phi, and y equals to b 1 minus cos phi. This defines your path for which the time will be shortest. I mean, this is the path for which the time is shortest for a falling object. You can think of as a falling ball, and these two equations generally represent a cycloidal motion. So when a body is falling under gravity in a frictionless surface, then from higher position to a lower position, then that the path which it will follow will be a cycloid, not a straight line or not any other thing. So it is called the Brachistochrone problem. It is a very famous problem, and if you search that Brachistochrone problem in YouTube, you will find many videos, interesting videos, where you can see that 3 balls are dropped from a particular position, released from a particular position. One is along a straight line, another is along the cycloid path. The cycloid path, the ball which follows the cycloid path, that will reach the end point faster, because that is coming from the extremization of time, shortest time. Okay, so this is the main motto of the problem, to get you some idea. Okay, so this is which I have shown here is the cycloidal path for which the time is shortest. Okay. Just go through the problem step by step, and you will reach the result. It is just to identify which is your actual f in the identify the f according to your problem. That is the main part, first part, and the second part is just do the just put it in the Euler's equation, and you will get the result for any of the problems. Okay. Okay. Now this was related to the variational principle. Now all the other important variational problem related to variational principle I have done in the last video. You can go to that. Now we will do some problems, not problems, some basic idea. I will try to give you some basic idea about the phase space diagram, because I have seen that sir have mentioned the phase space diagram and drawn some example, phase space for some example. Okay, so here we will consider 3 different examples. So first, that is ball which is thrown vertically upward. It is not a projectile. Here the angle is 90 degree, and you are just throwing the ball straight over your head. Okay, that type of problem. So for that, what will be our phase space diagram? Now you all know that phase space diagram means a diagram for a system which is in the QP space, QP space, where it is P and it is Q. QP space, where P is actually the momentum and Q is the position. So if if there is a point in the PQ phase space, that denotes the situation of the whole system at a particular time. Okay, so it and this point can move in direction, move with time. If it is at t equals to t0, say this is the position. At t equals to t1, the position can be changed. That means the system has also evolved. Okay, so that change, the evolution of the system is denoted by to different point in a phase space diagram. Each point in the phase space diagram denotes the whole system. Okay. Now a ball thrown vertically upward. Okay. So what is the situation, real situation? So suppose at t equals to 0 you are throwing the ball. So at the time when you are just throwing the ball, you are giving it a velocity. Okay. So that velocity is plus v. Why I have written plus v? Because I have considered the minus z direction in the negative side and plus z direction in the I mean opposite side. So if it is directed along the gravitational force direction, it is minus z cap. That's why I have taken it plus v. So if you can write that plus v z also. I was just focusing on the value, although it is a vector. So so it is v. Then the momentum is mv, and at the time of throwing, the displacement is 0 because that ball is just in your hand. Okay, it has not covered any distance. So at t equals to 0, p equals to non-zero, and your q equals to 0. Okay, q is the displacement and p is the momentum. So your phase space diagram will start from this point, where it is denoting that I have a positive p, which is plus mv, and 0 displacement. Okay, then it will evolve along this line which I have drawn, and at the highest distance, so after at t equals to t dash, you can say that at t dash it has achieved the highest point. So at highest point the situation is there is no velocity, the velocity is 0 because it will just stop there and then it will start to fall down. So the velocity is 0 there, but it has covered a certain distance or displacement, what you say, from the point from where it has been thrown. So if the distance is capital H, that means a non-zero distance, capital H, small h, nothing matters. So at that time the distance is non-zero and the velocity is 0. So this point denotes the situation of the particle at the highest point. Okay, where you can see that p is 0, momentum is 0, as well as velocity is 0, and the displacement is non-zero. So here as I written, displacement is h. Okay, so that is the displacement. Now what will happen? Now after achieving the maximum distance, it will start to fall down. So in that case, its velocity will be reversed. That means plus v velocity will be minus v velocity because it is directed downward direction. And at the time when it reaches your hand again, the displacement is again 0, but the velocity just before it touches your hand is minus v, as well as the momentum is minus mv. So this is the point which denotes the end position of the particle. That means you are getting a non-zero negative momentum as well as velocity and a 0 distance because it has reached your hand again after achieving the highest distance. So this is the phase space diagram of the particle which has been thrown exactly vertically upward. Okay, so it starts from this point. At the highest point of its path, it is here in the phase space diagram, it is here, and at the lowest at the ending of his journey, the phase space in the phase space diagram, it will be here. So and accordingly I have given the arrow sign because it is going in this direction. After achieving, it is coming toward this direction. Okay, so this is the phase space diagram. Now I will here all the thing we have not done any calculation, just from basic idea we have tried to just get the shape of the phase space diagram. Here nothing, here I have not put any value or anything. I have just given you the shape of the sphere. It can be, so it can be that also, that depends on what is your exact value and how what is the distance v, but I was trying to give you the idea of the shape. The shape will be like this always. Okay. Okay, good. Now for a free particle in motion, how the phase space will look like. Sorry. So the Hamiltonian of a free particle can be written as not a free particle of a system can be written as the potential energy plus the kinetic energy. So the kinetic term is the p square by 2m and Vx is the potential term. Now as I mentioned, it is a free particle. So just a second. Yeah, so as I mentioned, it is a free particle. That means there is no potential. So Vx equals to 0. Your only equation is H equals to p square by 2m. Now for this type of system, your H, which is the Hamiltonian, is actually the total energy of the system. So in place of H you can write E also. So that I have done, that P is coming out to be plus minus root over 2m. Now you can see this P is not a function of Q. Okay, that means you have a xy plane and you want to plot a function y equals to constant, which is not a function of x. So y yeah, so just a second, p y equals to constant. Yes, so y equals to constant means this type of line you will get in your xy plane. Okay, similarly here, as p is not a function of q, our in the phase space diagram, that p will be just a straight line parallel to the q, because it is independent of q, and depending on the value of energy E, so depending on the energy, it the position will be fixed. So if it has I mean, if it is E1 energy corresponding to E1 energy, now suppose you have another particle which has energy E2 which is greater than E1, then for that it will be parallel but at a higher position, because the E has been increased. Okay, but it will be straight line which is parallel to the q axis, as p is not a function of q, and as well as the minus 2me. Now you can think of the from where that minus 2me is coming up. So it is, I mean, suppose your particle is bounded by some wall. So at first it is going in this direction, and after the purely elastic collision it is just traversing it I mean direction. So when it is in the from left to right direction, this one, then it has the velocity, if it is plus v, then for the next term the velocity has been traversed, that is minus v. That's why that plus and minus sign are coming. It is you can think of that here is wall. I mean, this diagram, if you bounded it by these two sides, it becomes the diagram for free particle, not a free particle, I mean a free particle in motion but bounded by two walls. Okay, so that's why that plus sign and minus sign is coming into the picture. It is just the notion of direction. I mean, if at first v is plus directed in plus direction, in the second case after reflection from the wall of the container or whatever, it will take the value of minus v. Purely elastic collision I am considering, so there is no velocity loss or energy loss, anything. Okay, so this is the phase space diagram of free particle. So this type of question generally is very good question for exam. You can find some question like this also in exam also. Okay, so now coming to the damped oscillator. Okay, so when there is no damping, that part sir has already done. If there is no damping, so you can write is A is equals to p square by 2m plus half k x square, and that will give you a ellipse in the phase space PQ. Okay, so this is the phase space for a simple harmonic oscillator where there is no damping. Now if there is damping, that means the energy of the system will decrease with time. I mean, damping means that damp oscillation and forced oscillation we have done, that for forced oscillation it the energy is not decreasing, but for damped oscillation something is damping the motion, that means it is decreasing the energy. So in that case it will not be a closed orbit. I mean closed like orbit in the phase space. For this it was a closed because the energy was constant throughout the time. But for damped oscillation, p square by 2m plus half kx square is not constant, and it is decreasing. That's why you can see that the system starts from this point, and after a revolution it is not again coming back to its initial position. As with time the energy has been decreased, it is going to a lower orbit. Lower orbit means in that orbit for which the radius is smaller than the previous case. So it is following a spiral type of pattern in the phase space. Okay, so this is the change which will have, I mean this is the difference between the uh, ordinary oscillator where there is no damping on and the damped oscillator. The energy, the main change will be in the energy. The energy will decrease as well as the phase space orbit will also uh, will not be a closed orbit, it will decrease with time. Okay, now so I think it is clear to you that everyone that how to draw the phase space. Now all this calculation, all this phase space, I am again telling you that I have done in a quantitative way, a qualitative way. I have not calculated anything, just I have tried to give you the idea of the shape. Now according to the problem, when you will draw, you have to take care of the values which have been given in the equations or in the problems, and accordingly you have to draw. Okay, now okay now coming to the tensor algebra, I will not do much about tensor because I have seen that in the I mean assignments also there is not much focus on the tensor, but some basic, very basic idea. So one problem like this has been given in the assignment. You can see that what will be the rank of this particular tensorial quantity, where gamma ijkl delta lq, delta is the Kronecker delta function and gamma or omega are two different tensorial quantity. Now as delta is the Kronecker delta function, so it is non-zero only when L and Q are equal. Okay, that means you can replace your this L, which is gamma ijkl, that L with Q. Okay, because only for that this is non-zero. So we can eliminate the delta function and we can replace the L by the Q, which I have done in the next line, and as the omega as it is I have written it. Now here in the second step you can also see that there is two repeated index, and you know repeated index means summation over that index. So now if you sum over two indices, that index will not be there in the final expression. Okay, so this q will be summed over and your final expression will be like this gamma, I mean I have denoted it by this gamma which is the combination of these two thing, and your focus, you should focus on the index. So your q has been summed over, so there will not be any q, that just that ijk from the first quantity and mnp from the second quantity. So you can see there is gamma ijk mnp in the last line. Now what is the rank of this tensor? So rank means number of indices actually. So you can see here the rank is 6. So this is this type of problem you may face. I mean you have to you will be given some tensors of nth rank, just say, and you may be asked to contract it with some delta function. So you will do exactly like this what I have done. Okay, so that type of problems uh, I have given, I have that's why I have put it in the notes, so that you can understand how this is coming. Now Now, a very small thing, very small important application of the tensorial quantity uh, is the cross product of two vectors. Okay, so that's why I think it is important to give you some idea about how we can write the cross product in terms of tensor. Okay, so suppose a quantity C, which is actually the cross product of two vectors A and B. Okay, so and A can be written as Aj xj, where Aj are the quantity, I mean the value, and xj are the unit vector. It is like this: A1 x cap, A2 y cap plus A3 z cap. Generally, how we write a vector. Okay, so that I have written in this summation form, in this index form, and B has been written as bk xk. Okay, and we are doing the cross product. So Aj and Bk, these are just values, because like this 2 x cap plus 3 j cap plus 5 k cap, suppose say A is. So this is A1, this is A2, and this is A3. So A1, A2, A3 are just values, scalars. So that's why I have just taken Aj and Bk in a side, and I have put that vector, which is the unit vector xj cross xk. Okay, this thing and this thing, and now the summation is over j and k. Okay, now one important thing, you should from here you should focus in this line. So our property of our unit vectors x cap, y cap, z cap for a Cartesian coordinate, that is x cap cross x cap or y cap cross y cap and z cap cross z cap is 0. This all you know. And if you multiply x with y, you will get z, y and z you will get x, and z and x you will get y. These are the properties of unit vectors, you all know. But the interesting thing is, all these properties, all these different properties can be written in a very compact way if you use the Levi-Civita symbol. So all this set of equations, all these properties can be written like this, that xj cap cross xk cap is equals to summation over I xi cap Levi-Civita ijk, where I is going from 1 to 3. So I will ask you to just expand this particular thing with, and just take j and k value as whatever you like, 2 or 3, 1 or 2, 1 or 3, and just expand the right hand side. You will reach to this result, this set of results. So this is a very important thing, that xi, let us say xj cross xk, where xj xk are unit vectors, that can be written as epsilon I j k x I cap. Okay. This is an important property, and you will see that in various vector calculation you will use this particular form of cross product of two unit vectors. Okay, so that thing I have used here. Xj cross xk is actually epsilon ijk xi. There will be a cap, and ajbk is as it is there, it was there in the previous line also. And now the sum is over I, j and k. Okay, so what we got cross product of two vectors A cross B is this. This is the same thing, I have just written it in a fresh way here. So A cross B is actually xi cap epsilon ijk aj bk. Now this part A cross B is also a vector. Now if you want the ith component of the cross product, okay, so ith component of the cross product, I mean A cross B with a subscript I, so that is given by epsilon ijk aj bk. Okay, because the summation over I is not there, because I am just focusing on the ith component, that's why there will be no sum. If I want to focus on the whole cross product, then I will be 1, 2 and 3 because other components are also there. Okay. So a cross b I, ith component of a cross product, is can be written as epsilon I j k a j b k, and a cross b, as it is a vector, I can write it as a C also, right. So Ci is actually I j k a j b k. So in this form I have written just to give you the idea of the vector transformation. So you can see in your in sir's class also, sir have established various established the formula how the tensor or the vectors generally transforms. So this is the transformation of vectors. So if you look it closely, you can see that here this is j, here it is k, and j and k is here. So in the right hand side, j and k are the repeated index, so it will be summed over j and k, and only the I which is not repetitive, I index will be left over, and that I is matching with the subscript I which is in the left hand side of the equation. So this is the, I mean, this is how a vector or a tensor transforms, because you have seen in I mean, what is the in a moment of inertia chapter also, that we got the angular momentum that was L. So in tensorial form, L was I omega, right. Now if you write it in in component form, so your Li will be I ij, I mean here I have written m instead of I, okay, I ij omega j. So here again you can see that in the right hand side your j is repeated index, that's why it has been summed over j, and only the I is left over, and that I is matching with the I in the left hand side also. So this is how a tensor transforms. Now if someone writes you like ai is equals to, let us say, some tensor ij bi, whether it is a correct transformation or not. So actually first you see what is the repeated index in the right hand side. So here I is the repeated index, I also repeated index, so it will be summed over I, and it will give me a vector with the index j. But in the left hand side it is a vector with the index I. That means this transformation rule is not a correct one, and this is not the correct thing. So this cannot be a transformation rule for a vectorial or tensorial quantity. Okay, if it was written as ai equals to I ij bj, then it will be the correct thing, because j will be summed over and this I will match with this I. Okay, so this is how you can actually understand how the transformation of vector and tensor are happening, and you will find some problems in the assignment also based on this method, which transformation is correct for the tensorial quantity or not. So I think if you understand this part, you will able to solve the problem here then. Okay, so this was all about the tensor. I think this much knowledge of tensor is good enough for this course at least. So I will not go into deeper in the tensor I mean tensorial behavior, that is itself and I mean itself tensor itself is a complete course, it can be. Okay, so I will not go there now. If now I think this part, which was mainly based on the last lecture, has done, and I want to do some revision problems from Lagrangian, because in the next week I think you have the exam, final exam, so it will be a good idea to get some to do some old problems. So I have taken 3 problems today, and in the next class I will also do some old problems. I will try to do some old problems also. Okay, so first we will see a application of Lagrange's equation. I have done many applications of Lagrange's equation, so you may find it it is not important, but just to brush up your memory, I am doing this. Okay, so all you know that Lagrange's equation is this, which is d dt dll del qj dot minus dll del qj equals to 0, where L can be written as T minus V for a conservative system, where T is the kinetic energy and V is the potential energy. This I think you all know and you have not forget it. So we will do a problem, a pendulum with a moving support. I mean the problem is like this, a lift which is going downward, and in at the roof of the lift a pendulum is attached. Okay, so that is the problem. That means the pendulum is also with its own oscillation, it is moving with the lift in a downward direction. So that is the problem. Now let us say that this is the roof of the lift at a time t equals to t, and so we will start like this, that it was the lift, say at t equals to z. At initial time the lift was in this position, that means it was in this position. Okay. And up at a time t equals to t, it has come to this position. So this position, this is the position of the lift at a time after some time of the initial time. Okay, so okay, so this is the problem. Now how we will solve using the Lagrangian equation. Now that capital X O Z, this capital Z is our inertial frame. Now xz is the position of the blob of the pendulum. Now this x can be written as L, which is the length of the pendulum. It is given that the length is L, and L sin phi. So x equals to L sin phi. It is very clear from the figure. This is the x equals to L sin phi. Okay. Now coming to the y. So this part of y is actually L cos phi, but here the catch is, it is not the length which determines the position z of the pendulum, because z is actually this much, not this much. So this distance we need to add in our z. So that distance is, you all know, s is equals to half ft square, where s is the distance, f is the acceleration, t is the time. It is the very basic thing of the kinematics. The s equals to half ft square. Now that part we have added in our equation, in our position of z. So that is half ft square plus L cos phi. So if there was no lift and the pendulum was a static, I mean in a static system which is not moving, then this half ft square part will not be there. This is the main modification of this problem with the ordinary problem of pendulum. Okay. Now the kinetic energy T is half m x dot square plus z dot square, as all you know, and if you put x and z accordingly with differentiation with respect to t, so you will get this much, this equation, where phi dot is d phi dt, and your v is actually minus mgz. That means we have taken that at O v equals to 0 and it is negative from O. That we can do for our problems. So and we have substitute the z with the expression which we have got. So your L is done. It is just t minus v. So this was the t, this was the v, L is t minus v. Now just take this L and just put it into the Euler's equation. So d dt del L del phi dot, because you can see here the generalized coordinate is only one, that is the phi coordinate, no other coordinate is there. So d dt del L del phi dot minus del L del phi equals to 0. Now if you do it del L del phi dot, so you can see phi dot term is what happened, yeah, so phi dot term is this term and this term, that's why you are getting, and m is there, half m is there, that's why this half will cancel that 2 which will come down from the phi dot square, that's why m L square phi dot from this term. Accordingly you will get m f L t sin phi from that term, and phi dependent term is So this was all these two was phi dot dependent term. Now phi dependent term is this one and this one, right? Here cos phi and here sin phi. So that part will come into the del L del phi, and if you do it accordingly, you will get this result. So the final equation is this, that phi double dot plus g minus f by L sin phi equals to 0. So okay, so here one thing you should notice that as it is not a free fall, I mean the lift is attached to some string at the outside, that's why we have taken the acceleration of lift as f. Okay, and f is not equals to g. F equals to g means free fall, but for our calculation we have taken the lift acceleration of the lift is f, and the acceleration due to gravity is g, I mean g, that we have taken. Now if g and f is equals, then this second term will not be there, that will be only phi double dot equals to 0. That you can get from this equation also, what will happen if g equals to f. Okay, so now this is the equation of the motion of the pendulum which is moving with a lift. Okay, so this was just an application of Lagrangian method. I think it is clear to everyone. Okay, now just if you have any confusion, just go back to, I mean just scroll backward in the video and try to understand what I have said. It is simplest problem. Now another thing, so in your 10th, I think 10th assignment, I have seen that there are various questions on how to on the value of moment of inertia of different types of object, and I think all of the questions which have been given in the assignment I have done in my previous class also. So just go through those videos, you will get how to calculate and what will be the values of the moment of inertia. Just one thing I have not done there, but I have asked you to do that moment of inertia for a cone. So I thought that I can do it today in the revision class. So how to calculate the moment of inertia of the cone along different directions, and that cylinder, solid body, a rectangular lamina, a rod, I mean linear rod, all those I have done in the previous tutorials. So you can go through that. Okay, now coming to the moment of inertia of a cone. Okay, now first of all the necessary two equation from Cartesian to cylindrical system. So we will consider cylindrical system for this for our calculation, and the conversion is x equals to rho cos phi, y equals to rho sin phi. This type of conversion which connects your Cartesian to cylindrical or Cartesian to spherical, this you should remember and you should write at any time. Okay, so this you will need. Now okay, now consider this triangle. Okay, this triangle. So from in this triangle we can write rho m, which is this, by r is actually this distance which is z by this whole distance, okay, which is h. So this we will need in our calculation. It is similar that I have done in my previous class when I have calculated the moment of inertia for a triangular lamina, not a rectangular lamina, triangular lamina. It is the same type of problem. So rho m can be written as capital R Z by H, which I have written here. So this is important, this we will need. Now first we will calculate the IZZ, and after all that, I mean after all the classes and everything, you now, I think you can now write what will be the expression of IZZ or IXX or IYY in the integration form. So it is the expression x square plus y square dm, where dm is the mass, and that can be written as rho 0 dv, where rho 0 I have taken as a density. So never confuse between this rho 0 with this rho. This rho is the radial part, that is coordinate, but this rho 0 is the density of the cone, and I have taken as it as a uniform density, so it is a constant density cone. And dv, the volume element, can be written as rho d rho d phi dz. Okay, so never confuse this two rho, between these two rho, these are different. Okay, so this dm we will put in our expression, just put this, and x square plus y square. Okay, so x equals to rho cos phi, y equals to rho sin phi, that means x square plus y square equals to rho square just. So that's why I have written rho square. Now just do the integration with proper limit. So your phi limit will be 0 to 2 pi, z limit, which is the vertical direction, will be 0 to h, and our rho, and the limit of the rho will be 0 to rho m. Okay, so 0 to rho m. Now if you do because we are doing it 0 to up to from 0 to rho m, and later we will relate our rho m with the z. Okay, you can see here there is a small z, so we will relate our rho m with z after this particular integration. So this particular integration will give you rho to the power 4 by 4, which is rho m to the power 4 by 4 after putting the values. So it will give you rho m to the power 4 by 4, just this part, and in place of rho m we are putting r z by h. So you can see r z by h to the power 4 in place of rho m, and this 4 is here, this 4. Now we will do the z integration, because our rho was a function of z, that's why we have done the rho integration separately, and we will get an expression containing z. Now we will do the z integration with and the phi integration is independent, that will give you 2 pi. Right. So now if you do the integration, it is your result. So no problem, there is no problem if you just keep it as your result, but to get some more physical idea, we have done some algebraic manipulation as we always do. So 1/3 pi r square h rho 0 is actually the mass of the whole total cone, because 1/3 pi r square h is the volume times the uniform density, that is the mass of the cone. So we have written this separately, and for that we have to adjust the factor which will come in here. So I think yes. Now because just we want to express our izz in terms of capital M, that is the main motto of doing these two steps. So that is 3 by 10 m r square, where capital M is the mass of the cone and r is the radius of the base of the cone, although it is done in a opposite way, but r is the base of the cone, radius of the base of the cone. So you got your izz set. Right. Now we are calculating the ixx. So ixx similarly will be y square plus z square dm, where dm is again that volume element times the uniform density. Now the main difference will be here. In the previous case it was x square plus y square, which was just rho square, but now we have x square plus z square, and x square is equals to rho cos phi, rho sin phi, rho square sin square phi plus z square is z square. Okay, because I have not written here, so z is equals to z, there is no this is the conversion of cylindrical to Cartesian. Okay. Oh, that's why I think it is y square, sorry, y square equals to rho square sin square phi plus z square. Okay, so that we have put here this expression, and just do the integration as we have done in the previous case. Just separate these two, one is this term with this volume element, and second one is z square with that volume element. So I have separated into integration and just do the same thing, same way, just do just how I have seen that. First do the integration over rho m, then put rho m equals to rz by h, and then do the z equation. So if you do this separately, you will get all this expression. These are pretty easy to do, and again we are interested in writing our answer in terms of the mass of the cone. That's why 1/3 pi r square h rho 0 we have taken separately. So it will be your result for I ZZ, right? IXX. Oh, IXX I've done. IXX. So it is 3/20 capital M R square plus 4 H square, where R is the radius of the base, H is the height of the cone, and M is the mass of the cone. And as it is symmetric over Z, I mean this body is symmetric with respect to Z, so your IXX and IYY will be similar. So no need to calculate the IYY separately. So IXX plus equals to IYY equals to 3/20 M capital R square plus 4 H square. Right? This is the result. Just the main thing is just doing this integration properly with by taking in the transformations between coordinate system in a proper way. Nothing much, you will get your result. Okay, so this was thing. All the other types of system I have done, just go to those old videos. Okay, now we will do a very small but very tricky problem, I will say, of central force. Okay. So when the problem statement is like that, like this. So this is your earth, this is your earth, and it is a satellite, it is a satellite that is moving around the earth, but it is not in a circular orbit, because it has a smallest distance, I mean closest distance of 1000 kilometer from the surface of the earth. Note this point, from the surface of the earth, not from the center of the earth. So it is 1000 kilometer from the surface of the earth, and the farthest distance is 2000 kilometer from the surface of the earth again. So you have, and it is the problem, and you have given the average earth moon distance. Earth moon distance is given, period of moon is also given, and earth radius is given. Now you have to calculate the period of the satellite. Okay, so what we will do, here comes the Kepler's third law, which we have already read, that time period is proportional to cube, time period square is proportional to cube of the semi major axis. Okay. Now for this satellite we have to first found the semi major axis. What is the value of the semi major axis? So it will be, this total distance is 2a, which is 2 times semi major axis. Now this 2a is actually this 2000 kilometer plus this 1000 kilometer plus the diameter of the earth, right? Now radius is given, diameter is 2 times radius, so that's why 2 into, and you can see here the radius is given 6370 kilometer. So this diameter we need to add with the 2000, I mean farthest and closest distance, which I have added, and it come out as this is the expression 15,740 kilometer. This is the 2a, which is the twice of the semi major axis. Now the semi major axis a is just half of this, which is 7870 kilometer. Now you got the semi major axis for your satellite. You have given the semi major axis for your earth moon distance. Given average earth moon distance means we will treat it as the semi major axis. Okay, and your period of moon is given. So if your t varies a cube, that means t satellite by t moon square is a satellite by a moon. So that is the reason why the average earth moon distance or the period of moon is given so that you can compare the between those two and you can get your result. Now as we have calculated, am is already given, tm is already given, and from there we can calculate the ts, which we have calculated that using all the other data which has been given in the question, that it was 27.3 days moon period, that we have put the 27.3 and you will get the result as 0.0801 days, and if you convert it in hour, minute and second, this much you will get. Okay, so this is the application. This is a very small application but a very nice example how to calculate the time period of a satellite. Now, as an extension of this problem, you can also calculate the distance of a geosynchronous orbit. This is important for space science, because geosynchronous orbit are those orbit which have a time period of 24 hours. That means it is the time period is same as the time period of earth itself. So earth's time period is 24 hours. Geosynchronous orbit has also a time period of 24 hours. So we will calculate that. Okay, from this equation, as from this equation, it can be written as cube ts square by tm square into am cube. Here also we will use the data for moon which has been given in the exam. So your in the problem, not exam. So your as can be written in terms of like this: a is equals to am ts by tm to the power 2/3. Okay. Now for this case, your ts is given, which I told 24 hours or 1 day. tm is given in the question, that is 27.3 day I think, and am is also given, which is the average distance between the earth and moon, this 3.84 into 10 to the power 5 km. So if you put all this value, you will get the as, which is the distance of geosynchronous orbit from the earth's center, is 42,354 kilometer, and it is from center. So if you calculate from the surface, then you have to just deduct the radius of the earth, which is given 6370 kilometers. So this is the distance from surface of earth. So in this way, there are many this type of small problems which you can calculate. So distance of geosynchronous orbit you find, you just calculated, and time period of a other satellite which is not geosynchronous, for that we have calculated the time period using the moon earth distance and time period of moon as the base of our calculations. So these three problems from, I mean, what from those topics that was covered in the earlier videos, I have tried to cover, and I will try to cover some more problems from these chapters also, just as a revision of your upcoming exam. Okay. And as well, I will also do some problems related to the new topics which has been taught in the has been taught in the class also. So I think I will stop here, and if anyone have any question, you can ask. This was another problem which I has been solved in the previous videos also, but for the tensorial application, I mean for I have put it in here, so I have been done in, and it is a problem from your assignments. Just you can check it also. Okay, then we will meet next week, same time, and thank you.